Welcome to the last of the field effect transistor series. Like many third sequels, this one is the most hastily put together, low budget, but you'll watch it anyway because it's the third sequel. Anyway, let's go on. So MOSFETs are interesting, and I hate to mess with your head after all of the clarifications with JFETs, but MOSFET gates behave differently from those of JFETs, and it's somewhat counterintuitive. And the reason for that is because of how MOSFETs work and how the operation of a MOSFET is actually different than a JFET fundamentally. This is a picture of a MOSFET. You'll see that the gate is actually not in contact with the channel material. So this would be a p-channel MOSFET, and you can see that the gate has an oxide layer between it and the p-channel. And that's what makes a MOSFET categorically different. You are no longer able to pull charges out of the P region through the gate. Rather, you've got what is essentially a capacitor, where the oxide layer is like your dielectric in between two plates. The one plate being the gate, and the other plate being the P channel. So, as I said, the gate is not in electrical contact with the semiconductor. There's a metal oxide layer between. If you remember when we talk about how JFETs work, when we're reverse biasing the JFET, we're actually pulling positive charges out of the gate and negative charges out of the source, thereby expanding or growing the depletion layer and choking off the current. And obviously, we can't run a current through the gate when we're reverse biased, but we can pull those charges out and sort of stretch the depletion zone much the way that we do in a diode. But that's only possible because the gate is actually in physical contact with the P material, the gate electrode. In a MOSFET, you can't do that. What happens instead is you're using electric fields to move charge carriers around. If we go back to this picture, when we put a positive bias on the gate, we're actually pulling extra negative charge carriers into the P region, and those charge carriers go up to the to where the plate is, because if you've got a positively charged plate, then you're going to get a negative charge on the other side, hence the sort of capacitor-like way of looking at things. So if we apply a positive voltage to a p-type material, it pushes away positive charge carriers, leaving a negative depletion region. And similarly, a negative voltage applied to an n-type material pushes away the electrons, leaving a positive depletion region. In a MOSFET, we're not pulling charge out of the semiconductor through the gate to make a depletion region. We're pulling it in from the source. And this is like charging a capacitor. So let's actually see this in application. So here's a depletion mode MOSFET. If you remember, a depletion mode MOSFET is one where you have a continuous channel. So the N channel goes all the way from source to drain with nothing intervening in between. If I apply a positive charge to the gate, I'm actually going to be pulling more negative charge carriers into the N-type material. So I'm enhancing the number of charge carriers, and therefore I'm making it more conducting. If I apply a negative electric field to the gate, then I'm pushing away the negative charge carriers in the N-type material. They're going to go out the source and the drain, and the density of negative charge carriers in the N channel is going to be fewer, and therefore it's going to be less conducting. If I were to draw this out as a function of VGS, making VGS more positive enhances the conductivity, so that's the enhancement side, and making it more negative depletes and eventually chokes it off. So it looks kind of like a JFET in the sense that when you're going for this N channel, at least, there is a way that would go to zero. So a depletion mode MOSFET, its default state is that it does draw current, but not only can you affect the gate voltage to reduce that current, you can also enhance the current. And that makes it different from a JFET, where you can only reduce the current. Similarly, with a P-channel MOSFET, if we put a negative voltage on the gate, then we bring more positive whole charge carriers into the material, and that enhances. So negative voltage enhances, positive voltage eventually chokes off the current, as is illustrated in the curve that I painstakingly remade. And yeah, so you can see that effect. Now, those are depletion mode MOSFETs where the channel is continuous. In an enhancement mode MOSFET, the channel is actually cut in half. So our N channel is cut into two by the P channel. And what happens essentially is at zero gate voltage, no current can flow because you've got to get the charges from the N channel across that P channel. But if you apply a positive voltage to the gate, if that voltage gets large enough, then essentially you're going to pull in enough negative charge carriers and push away enough positive charge carriers in the region of the gate to create a channel through which to flow the current. And so unlike the depletion mode MOSFET, the default state isn't to allow current to flow. Rather, you have to keep applying this positive voltage in the case of an N channel to flow current, and in the case of a P channel, you need to apply a negative voltage to pull enough positive charge carriers to create a pathway for current to flow through the N-type material. And that's it.